All right, for question number 2 in section 13.6, we're going to look at some more directional derivatives. But here we'll see that the directions that are indicated are not given as unit vectors. So we're going to have to make an adjustment. Okay, so here we have in part A the function g of xy, which is the log of x squared plus y squared. And we're going to differentiate this function at the point P with coordinates 2, 1 in the direction of the vector v that's equal to negative I plus 2j. All right, so the first thing I want to note here is that this vector v is not a unit vector. Okay, so if I take its magnitude, in other words its length, I get the square root of 5. Okay, so this thing is not a unit vector. So then what do we do, right? Well, what we can do is simply consider the unit vector that points in the same direction as v, and I'll go ahead and call that vector u. Okay, so what is u equal to? Well, u is just going to be a scaled version of v because they have the same direction, and in fact if I just divide v by its own magnitude, so 1 over the square root of 5 times the vector v, this thing will have unit length. Okay, and you can certainly check that by just computing the magnitude from the coordinates there, or you just as well can just think about, right, what this statement right here is really saying. We're just scaling v down by its own magnitude. So this thing is a unit vector. All right, great. So now let's go ahead and compute the gradient of our function g, because we're going to need this to compute the directional derivative. And so here I need the partial derivatives of our function g here. And for the x derivative, well, I'm differentiating a log, so that'd be 1 over what's inside the log. And then I'm going to multiply this by the derivative of what's inside with respect to x. And that's going to give me a 2x, which I'll just put up in the numerator. And then the y derivative is really essentially the same thing, except we're just replacing y where I see the x there on top. Okay, great. So now let's go ahead and compute this directional derivative. So I'm going to say the derivative of our function g at the point 2, 1 in the direction of, well, v, which is the same as the direction of u, the unit vector. This is going to be the gradient of our function g evaluated at the point 2, 1 dotted with this unit vector u. And plugging in 2 for x and 1 for y here, I'm going to get, for the components of our gradient, we'll get 4 over 5 and then 2 over 5, and we're dotting that with the vector u, which I'll go ahead and write with these angle bracket notation just to be consistent. So this would be minus 1 over root 5 and 2 over root 5. All right, and so now taking this dot product, I'm going to get negative 4 over 5 root 5, and then I'm going to get plus 4 over 5 root 5. Oh, and these are going to cancel out, giving us a derivative that's equal to 0. Okay, so let's recall again what this directional derivative is really telling us, right? We want to think about, right, we're standing on the surface z equals g of xy directly above this point P, and then we're going to start walking in the direction of v, right? And what we're seeing here with the 0 derivative, we're seeing that our surface is actually flat there at this point. Okay, so here's our point P down in the xy plane, and then we're up here on our surface, and we're walking in the, oops, sorry, that's a g of xy here, but we're walking in the direction of the vector v, which is equivalent, right, to just walking in the direction of this unit vector u. But the point is, right, that we are at a plateau, right? The derivative here is 0. All right, so that is part A. Very nice. Let's now check out part B. And here, notice we have a function of 3 variables, okay? So we're going to compute its directional derivative at the point P, which is in 3-dimensional space, right, with coordinates 1, 0, 1/2, in the direction of this vector u, which is I plus 2j plus 2k, okay? Now, first off, what exactly is the appropriate or inappropriate interpretation of the directional derivative in this context? Well, for functions of 3 variables like this, I think it's pretty natural to think about these things as telling us something, say, in about maybe like a distribution of some type of quantity. Like let's say, for example, h is measuring temperature throughout a room, right? So there's some temperature distribution, and this function h, right, is just like a little thermometer. It's just a gauge that, say, at this point P, right, you feed this function h its coordinates, and it's going to spit out the temperature at that point. So let's say we're located here in some room, and then we're going to start heading in this direction u, right? What our directional derivative is going to tell us now is just the rate of change of this temperature in the room as we move in the direction u, okay? So let's go ahead now and, just like we did in part A, first look at the direction vector, right? Is this thing a unit vector? And the answer there is no. So if I do the square root of, well, 1 squared plus 2 squared plus 2 squared, that's going to have a magnitude of 3, right? Because we get a 9 under the square root. So it's not a unit vector. So just like we did in part A, we'll go ahead and consider the unit vector that points in the same direction as u. And notice here, right, don't be misled by the notation. Okay, just because we're calling this original direction u does not mean it's a unit vector. Okay, so I'll go ahead and call this new vector, I'll go ahead and call it, well, v, right? Where v now is going to be the unit vector. And I can compute this thing by just dividing the vector u by its magnitude. So this would be 1/3 I plus 2/3 j plus 2/3 k. All right, so again, you can go ahead and check that this thing is in fact a unit vector by looking at, say, these components, or again, just think about what this statement is really saying. If the green vector has length 3, right, dividing the green vector by 3 is certainly going to give us something of length 1. So this thing now is our unit vector in the appropriate direction. So the next thing we'll compute is the gradient of our function. And for a function of 3 variables, well, we'll now have a vector with an I, a j, and a k component, and these will just be the partial derivatives as such. Oop, that's not a z up there. We want a h. All right, and so let's go ahead and do this. Now, here, I'll actually make a little space down here. So I'm going to take the x derivative. Now, one thing I notice here, just that will slightly simplify the computation, with a log like this, it's a log of a product. So this thing is really the sum of these logarithms. Okay, so this isn't going to like greatly simplify things, but it'll make the derivatives of this last term a little bit simpler. Okay, so now with that in mind, What is our x derivative? Well, I have an x here in the cosine term, so I'm going to do, well, from the chain rule, I'll do the derivative of the outside, so that'd be minus sine, and just for emphasis here, I'll say x, y in parentheses there. And then we have to multiply by the derivative of what's inside with respect to x, and that would be just a y. Okay. Now there's no x in the e to the yz portion, so this would just be 0 there for the x derivative. And then lastly, differentiating the log of x there, that would just give us 1 over x. The derivative of the log z part would be 0. All right, so that's our first portion. The y derivative, pretty similar. We're going to have our minus sine of xy times the derivative of what's inside with respect to y, and that would be x. And then here for the exponential part, I'm going to have plus e to the y z, and then times the derivative of yz with respect to y, and that'd be a z. And then lastly, the log terms, right, they would have a derivative of 0 when I differentiate with respect to y. Okay, and then last up is the z derivative, so this first portion then would be 0. Here I'm going to get a e to the y z times y, and then I'm going to get my plus 1 over z. Okay, so a little lengthy there, but that is our gradient vector. And now we can go ahead and compute our directional derivative, where now I'm going to say the directional derivative of the function h at the point 1, 0, 1/2 in the direction of the unit vector, which we're calling v. This would be our gradient evaluated at 1, 0, 1/2 dotted with that unit vector v. And so now I want to go ahead and plug in 1 for x, 0 for y, and 1/2 for z. Unfortunately, a lot of this is going to clean up quite a bit. So let's see. Notice plugging 0 in for y, this both the sine term is 0 and just this y term is 0, so that drops out. And then I'm plugging 1 in for x. So I'm just going to get a 1 there for the I component of the gradient. Okay, for the j component, well, the sine part's still going to be 0 because y is 0. And then I'm going to get an e to the 0, which is 1, times z, which is 1/2. So that's going to give me 1/2 for the j component. And then last up, we have e to the yz times y. Well, if y is 0, that's going to be 0. And then I have 1 over z. I'm taking the reciprocal of 1/2, so that would be 2. All right, and then I'm taking the dot product of that with our vector v, which we computed over here. This is 1/3, 2/3, 2/3. All right, and just about there, we can go ahead and now take this dot product, so we can get 1/3 plus another 1/3 plus 4/3. So that's a total of what? 6/3, so 2. All right, and so that would be our directional derivative. So again, if this was, say, you know, h is computing the temperature at a certain point, right, then we'd be saying that the temperature would be increasing at, say, the rate, you know, 2 degrees Celsius per meter as we move in the direction of this vector u. All right, great. We'll stop there.